All right, so the topic tonight is reinforcement learning. So let's dive right in. A lot of you probably haven't heard of it before, so let's talk about what reinforcement learning is. And the best way to do that is to draw comparisons to the other types of learning that you've already learned about. So we've learned about supervised learning, where you know what the target is, so you know what value it is in regression or what class or classification, and you train a model to basically guess correctly or predict the right value. Then we have unsupervised learning. This can create clusters or groups for data that's not labeled. And then kind of the third option is reinforcement learning. So reinforcement learning is more about decision making. It's about choosing actions that can lead to maximizing potential rewards in some system. So this could be in like a factory line, it could be in a game, it could be in the stock market, lots of different scenarios. So some of those applications, like I mentioned, training robots, so getting them to pick things up, put them down in the correct location, things like that. Actually optimizing chemical reactions. This can be done with reinforcement learning. There's a lot of different potential ways to kind of put chemicals together and to kind of synthesize things. So sometimes finding the optimal way isn't always super easy or straightforward, but reinforcement learning can kind of figure out the best path for that. Traffic flow. So figuring out how to manage, really heavy traffic, busy intersections, where there's a lot of different roads like you see here, finding the optimal way to set that up. The big one, autonomous vehicles, teaching a car to stay on the road, rewarding it when it does, and then encouraging it not to, hit pedestrians or go off the side of the road, stuff like that. And then the big one, and this is kind of the sandbox that reinforcement learning uses, is video games. So we've seen things like in the top here, AlphaGo, AlphaZero, learning to play games like chess, traditional board games. In the bottom left, AI has been able to play old Atari games like Breakout. And then even on the bottom right, some more modern games that are a little bit more complicated. This is Dota 2. OpenAI was able to build a bot that can actually play this against pros and actually beat them, which is pretty impressive. So how does it work? Well, at the core, there are 5 main components. So the first is the environment. This is simply the world that everything else lives in. So it's the video game, it's, the streets and the roads for autonomous vehicles. It's basically the whole world where all the different parts and the players and pieces are in. Then we have the agent. The agent is basically the AI or the player or the model that's trying to improve its performance in the environment. Then we have states, which are different configurations of the environment. So if we're trying to self-drive a car, one environment is there's a car in front of it, another there's a car behind it, another there's a car in front and behind it. So in some environments, there can be millions and millions of possible states. Then we have actions, which are just all the different moves that an agent can make at any given state. And finally, how we improve performance and optimize the bot are rewards. So positive or negative feedback values, depending on the changes to the environment that occur as a result of the actions of the agent. So this is a kind of simple flowchart diagram that shows how these play together. So we start off with the agent, so our AI. It chooses an action. That action affects the environment, changes it in some way. And after that change, we can check what the reward is. So whether that was a good or a bad change. And then we also get a new state. So the state changes. And we pass that state and the reward back to the agent. The agent will do some modifications, try something different, and then repeat. And this basically loops over and over, continuously improving the agent's performance in attempts to maximize the reward that it gets. So for a simple example, imagine we have a game here where there's a penguin in the bottom left. It's trying to get to the fish in the top right. It has to move through these ocean squares while trying to avoid the mines or the shark. So in training this penguin to try to get to the fish, we need to assign some values to the different spots that it can end up in. So for example, if the penguin moves to an empty ocean space, that's a good thing because it's still alive. So we should probably reward it a little bit. So we would give it a reward of +1 if it moves to an empty blue space. If it tries to hit a wall or go outside of the arena, that shouldn't be encouraged. It's kind of a bad thing. It won't kill the penguin, but it can't really do that. So we'll give it a small negative reward, -1. If it lands on a shark space and gets eaten, that's really bad. So it will lose 50 points if it lands there. And if it lands on a mine, it'll blow up and probably blow up the other mines too. So that's really, really bad. So that's -100. And finally, the goal is to get to the fish. So that we should reward greatly by giving the penguin 100 points. So that's kind of the reward system we set up. Usually you'll have to decide on things like this, what to encourage, what to give negative rewards for, things like that. And this all centers around what's known as Q learning, which is basically learning a way of choosing actions that will lead to the highest rewards. And Q learning uses this equation here, which will look kind of complicated, but I'll break it down. So on the left is just what's known as the Q value. So this is reflective of the rewards that will be granted by choosing a certain action, and then also including the maximum possible rewards of the next state. So the RT is the reward for taking the current action. So that's right here. So whatever action we take, we check what reward we would get for that. Then the next part, if I can, there. Next part, this symbol, it's gamma. So this is a discount factor, which we'll get to in a second what it's discounting. It's discounting this max Q ST+1, AT+1. So what this is basically the maximum Q value of the next state. So we make an action, we check the rewards we got for making that action. Then we look at all possible actions in the next state and choose the one that will give us the highest Q value. And that's kind of our max Q, our best next move, basically. And since that's not like a definite thing, since it's in the future, you know, it could actually be less than that. We don't know. That's kind of just our best guess. We give it a discount factor known as gamma. So what this does is train the AI to not only look at the action that will give it the best reward currently, but the action that will lead to the best rewards overall, kind of in the long run. So it kind of enables it with this max Q of the next state. It allows the AI to kind of look forward a step. So if it could get a reward of 10, but then next turn, taking that action would lead it to a state where it could only get 1 point. So then you'd have 11 overall. Or it could take 2 points now, but it could get 20 if it chose that action in the next state. So kind of teaches it to look ahead and make better decisions for the long run. All right, so to use that Q function, the simplest way is to implement a Q table. A Q table has every possible state listed down the left side, and then across the top are all the possible actions at each of those states. So at any possible state, the penguin could move up, right, left, or down. And then the states here, we'll just kind of, let me draw one here. So we'll say this is 0, 1, this is 0, 2, so on and so forth. So in using this equation, we could start having our penguin move. So he's going to move to this spot here. And let me switch the color so that you can see that better. So he's going to move to this spot. If you remember on our rewards table, moving to an empty ocean space is +1. So that's this part here. So we get 1 point for the current rewards. So now we're in this next state, and we can kind of look ahead. So we could either move up, that would be onto the mine, and that would be minus 100 points. We could move to the right, and that could be +1, or we could move to the left, back again, and that would also be +1. So our gamma, our discount factor will maybe do like half. So if we move to this spot here, our next maximum possible move would also be +1, which multiplied by the discount factor is 0.5. So then this all equals 1.5. So then we would go to our Q table, find the state that we were in, which was 0, 1, and we moved right, and we would update this to 1.5. Then the penguin would, probably move this way so that it doesn't backtrack, and kind of repeat the same process. And over time, it'll basically fill out this whole table. And over many plays of the game, it will fill in all the values. And in doing that, it will find the best path to the fish. In this case, there's no penalty for kind of taking extra time. So really the penguin, could go up here, come back down, kind of loop around forever collecting points and then finally ending on the fish. So usually you want to give some kind of penalty for number of turns taken so that then the penguin will end up going straight for the maximum reward or the end game. So that's kind of how you would do a Q table. This is something you could do by hand or just in Python. So we're going to actually go into an activity here using that. So you all installed Gem, which is a really cool library for Python that allows you to basically interface with various games. And they have it all designed for reinforcement learning. So it's really easy to work with. You can step through the game action by action, get the rewards really easy. And you can also watch the agent play the game while it's learning, which is cool. So these are kind of a lot of the games that are included. It has Atari games, which are more difficult to train. It also has some more simple games like text-based ones, which is actually what we'll be working with, that are easier to train. And on the top right, you can see kind of a simple setup. So this would make this game called Cart Pull. And for 1,000 turns, it will display it. So that's what environment.render does. And then the step means it's going to take an action, and passed into that is basically a sample of all the possible actions. So this would take a random action for 1,000 turns and basically play the game for that long. And we'll get more into depth in that. So we're actually going to switch gears here. Let's see. Let me switch to this. We're going to be in the Frozen Lake exercise notebook. I'm trying to bring up the chat, but I can't. I think I saw somebody said something.
That was I don't know if my mic, it looks like my mic's
Oh,
working.
there we go.
I had a question about the time and the steps. Is that just subtracted from the Q function?
So actually, it would probably be for every blue square we go on, we'd give it a really small negative reward, like minus 2.5. Something that won't, make it not want to move at all, but something that, the more steps it takes over time, it will basically lose points.
Okay, so you incorporate it into the reward system.
Yep.
Okay.
Yeah, the reward system is kind of the only way that you encourage or discourage different actions.
Okay.
Yep. All right, can everybody see this? And does everybody have this notebook open? Okay. So the game we're going to play is called Frozen Lake. The board is set up just like this. There's only 16 squares. The squares have 4 different possible states. If it's an S, and you'll actually see it in this format text. If it's an S, that's where the player starts. If it's an F, it's frozen ice. The player can move on it. It's a safe spot. If it's an H, that means death. Basically, the person will fall in through the ice into the water and the game will be over. And then finally, G is the goal. So the goal is just to get this guy to walk down on the safe ice and end up at the goal. So this notebook is basically all set up for you guys. This first part, you're just going to run this stuff. There's a couple questions to talk about. This next part has you actually implement the Q table. You basically add like 4 or 5 lines of code in here, depending on what the comment says. It's not too difficult, but I'll help you out. And this will basically have it play the game. Then we're going to look at the Q table. I should probably clear the output here. Then we're going to take a look at the Q table and see what it learned, and then a couple more discussion questions. And then for the solution, we'll come back together and kind of talk about it. So we're going to go right into breakout rooms. I'll hop around like usual, just kind of try to follow this through and do what it says. And we'll see what happens. So let's go ahead and pause. All right, so let's talk about what we learned. So do I have a volunteer to talk about the first part? So slippery equals false. Just kind of run through what you did real quick. Look at your Q table. Maybe Beth, would you like to do that?
Wait, what? What am I doing?
Share your part for the slippery equals false.
Yes, I can do that. Okay, so ignore these things. We don't need those. Please and delete. Okay, so after running the game, we decided that after 100 moves, our agent didn't really move from the starting area, and this environment maybe won't be the easiest thing to solve. We ended up doing some probability calculations, and after 2 moves, you only had a 16.5% chance to not die. So this wasn't the easiest thing in the world to do. This is our code. The things that we did after getting this information and figuring out what this all meant, things got a lot easier. So basically, this action, we're taking a random choice. We're looking at random choice based on a Q table and a maximum value. We're passing in that action here to our game, and we're receiving back some information, whether or not the game is done, the reward, and the next state. And based on that, we can figure out the Q value using this equation here. Then we pass that Q value into our Q table. We updated our scoreboard, and then we set our state to our next state. Then we appended our score to the global, kind of like this is how all the things have gone so far, and some information about how everything is running. And after we ran it, our little player action figure person, that I forget what the name of it is, actually succeeded, and we were excited. The way that we know he succeeded is because the word solved, but also the average after 100 games was over the value of 0, and it was not negative. So he died less than he succeeded. And we were able to get there in 132 episodes or plays or rounds of the game.
All right, awesome. And then your Q table, so it's mostly zeros, it looks like, except for basically 1 value per row, or sometimes no values per row has a value not 0.
Mm-hmm. And so for the Q table, we decided that this was probably up and this was probably left, and either one of these two were down or to the right. So each column in your queue table was going to be an action that the player can take.
All right, cool. So moving on to turning slippery on. So basically when the player moves, now the ice is slippery, there's a chance he'll go a different direction. So Brendan, if you could share what your group did for that.
Sure, for the one without the greedy epsilon?
Kind of just both parts.
Okay. Yeah, so when we ran basically the same code, what we found was because of the slipping, even when we did 100,000 games and tried to say, okay, let's not even try to get to 10 games. Let's try to get 4 games in a row where we win. It failed. We a couple times got where we could get 2 or 3 in a row and it would be solved, but I think that was just more random than anything. Pretty much what it couldn't do is it couldn't account for the random effect of the slipping. And you can see here that throughout the tries, it did win a few of them. So it did kind of find a path in there, but because it kept slipping, it wasn't ever able to recreate the path. So it would hone in, try 0.596, I would assume, if it was looking for the max Q value, slip and lose. And then kept trying to go along that way. So we went ahead and tried this greedy epsilon since the code was already all written for us. And what we found is it would solve it within 1,000 games pretty much. And as you can see, the Q table ends up looking a lot different because it's now doing that exploration because of the epsilon, and really mapping out a lot of the initial moves that it can make and assigning what's the most likely move for success using the Q values and kind of gradual way that it sets the Q values using the learning rate and the alpha at the beginning, so that it actually then once it's explored enough and it starts trying to make moves based on the reward system, it has a pretty robust base of a reward system that is allowing it to make the right decisions.
Yep, that sounds good. And I'll talk about the greedy epsilon and the learning rate here in a second when we go back to the PowerPoint. But yeah, so that's that activity. That's kind of a really simple environment, probably one of the most simple you can do. And we'll kind of see some others here in a second. So thanks for that, Brendan.
Sure.
All right, we're running out of time, so I'll go quickly through the rest here. So basically, now we can take this Q learning and throw it into a neural network and handle a lot more complicated environments. So this works by implementing basically 3 important things. The first is experience replay, the second is epsilon greedy policy, and the third is having a separate target model. So I'll kind of explain what those do a little bit. Experience replay is basically we keep a history of all the moves we made and all the rewards we got. And then every once in a while, we choose a random sample of that memory and train the network on it. So it's kind of like when you play video games, you don't just think about the previous time that you died. You think about all the previous games and certain ones come to mind and you kind of learn from them that way. So it kind of recreates that in a neural network. The second is a separate target model. So you basically have 2 networks. One you make predictions on, and the other is kind of your final model. So basically you make predictions on the one, and every once in a while you transfer the weights from that to your kind of base core model. So this basically, it basically allows things to kind of stabilize, because what happens when you do neural networks with Q-learning, things can kind of spiral out of control and the Q values can explode actually. So this kind of makes the updates a lot slower, and you only transfer the weights every once in a while. And then the third thing, this was used in the slippery solution. It's epsilon greedy policy. So basically we have a value called epsilon. It starts off typically at 1. And then each time we choose an action, we generate a random number between 0 and 1. If the number is less than that epsilon, then we choose a random action. Then after every move, we decrease the epsilon by a little bit. So it goes from 1 to like 0.99, 0.98. So what it does is that over time, the network will choose an action based on its prediction instead of random. So the idea is that it starts off making only random actions. It accumulates a bunch of knowledge, learns on that, and then over time, it'll eventually go, okay, I've learned enough. I'll start trying to make predictions on what to do now, given what I've learned. So this kind of helps with random environments because you can think if early on it encounters like a rare scenario where it slipped, it might base the rest of its learning on that particular game and give too much weight to it. So it gives a lot more stability to the whole process. And yeah, you basically have a value called epsilon start at 1 and you decay it by like 0.99, 0.98, something like that. So it gets smaller and smaller till at the very end it's 0 and you're basically predicting your actions each time. Let's see, and that's just kind of explaining more of that. So this is an overview of how it works for a DQN then. So you choose your action via epsilon greedy. You store the state, action, reward, and next state in memory. Then after some interval, you experience replay. So you look back on your memory and you pick some random examples to train on. Then you transfer your weights from your primary to your target model. You decay your epsilon. And then you basically repeat that over and over. So that's kind of the simple step-by-step, the process. This is a taxonomy of all the reinforcement learning algorithms. There's a lot. This is very much a new space, so there's always new ideas, new papers. There's probably more to add to this table than from when I first grabbed it. But in this, you can kind of see, this is DQN, that's what we were talking about. And you can see it's under Q learning, but there's basically a ton of others. I have them in here, a couple to talk about. The first is policy gradients. So basically for Q values, we're trying to predict rewards, but in policy gradients, we end up predicting actions. So if you look at the two networks, they look almost identical. In the DQN, you're predicting Q values, but in the policy gradient, you're actually predicting probabilities of selecting actions. It's kind of something you'd have to see in action, but it's kind of a variation on the DQN that can work better in certain environments. These are kind of some contrasts between the two. Then there's also actor-critic. So this basically, there's an actor and a critic. So the actor is like a traditional model. It chooses actions, it plays the game. And then there's a critic, a second network, that basically looks at the performance of the actor and basically tells it whether it's doing good or not. So basically you have two models instead of one. This solves a lot of problems in more complicated environments. It's a really popular solution for reinforcement learning nowadays. You'll see it referred to as A2C or A3C, and it basically stands for actor critic. This is a comparison of, this is actually an example of how reinforcement learning can go wrong. So this game, you'll see on the left, it's basically a boat game. The goal is to travel around. It's basically a race. There's power-ups though you can get, like those blue orbs. So you get points for those. So this is a human player. He's basically trying to catch up to the other people, trying to win the race. Well, they trained a DQN agent on it, and this is what it ended up doing. So it basically figured out that getting those power-ups gave it a ton of points. And the way they set up the rewards, they gave way too many points towards getting those. And so it basically stopped caring about winning the race and just kept circling around trying to get those turbos and accumulating a ton of points. So it kind of shows how there can be unintended consequences. If you're rewarding certain actions, the game might try to basically exploit them. And these are some of those challenges. Instability, it's computationally expensive. Training time can take weeks, actually, even on supercomputers to play really advanced games. It's very computationally expensive. It's also hard to reproduce. There's tons of randomness both in the game and in the network. And then also exploitation, like you saw. Sometimes the network figures out a way to basically cheat the game and behave in a way you wouldn't want it to. This is a really cool video. I'm trying to see if we're gonna have sound. Can you guys hear the sound? You can? Okay. We'll just watch a few minutes of this, or it's only 2 minutes.
Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observed, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other, as well as past versions of themselves, using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans.
But yeah, you get the idea. So it's really cool. This was done by a company called OpenAI. They're really awesome. I'd recommend you check out all their stuff. They do really fun projects like this. But yeah, the main idea is that the possibilities with reinforcement learning are really endless. Like it starts off with just video games, but you can imagine eventually it being implemented in real world things. So it's really cool. Here's some lectures that I like on the topic that are cool. A couple articles in there as well. And that is everything. Sorry, I know that's a lot, especially if you came into tonight not knowing anything about reinforcement learning, but hopefully that gives you a good introduction into the topic. And I also have something, if you want to work on something later, I included a lab actually in the style of like a Flatiron School lab. So you basically are going to learn to play the cart pull game. It's a little bit more, let's see if I can get it to play randomly. It's a little bit more complicated than the Frozen Lake one. You'll actually be able to see a video output of playing the game, but it's basically a cart moving back and forth trying to balance a stick and to keep it like upright. So it's pretty cool. It basically walks you through building the DQN, the neural network, all that. It's really fun. And I'd also recommend you just check out Gym. They have a ton of environments you can play around with, Atari, all different games. So yeah, really fun stuff.
Thank you.
Yeah,
Yep.
this is really cool.
Yeah.
Yeah, it's a fun one.
And I like your presentation.
Thanks. Yeah, that was actually my first study group I did for Flatiron was on reinforcement learning. So
I feel this is beyond my reach.
it's beyond mine too. Like I'll never really understand everything. I just think it's cool and I like playing around with it. So
Yeah, it's awesome.
yeah, you basically need to have a PhD to really do the high level stuff. So who knows, maybe someday.
Yeah. So Matt, our next week, are there any other study groups?
Yeah, so we do have a couple more things to get through. Can you guys see this on the screen?
No.
Let me. So this is just on Learn. Okay, so we have done 43 basically through 47 and then also 49. So I'm thinking doing one lesson Monday that kind of talks about 42 and 48 and 50. 42 is not super important. It's kind of all network and clustering stuff, but we can talk about it a little bit. The important thing is going to be transfer learning. We kind of got to see that a little bit with using the glove embeddings in the NLP lesson, but that's going to be important. And then this last part is kind of just about taking neural networks and, implementing them elsewhere or doing them in the cloud. So we might talk about that. I might show you guys how to actually make like a Flask app. So that lyric writer thing I showed you guys, that's just hosted on Flask. It's pretty easy to implement because it's all written in Python. So we'll maybe talk about that. And then I think next Wednesday, basically start capstone topic searching. So we can meet, talk about it, go over the actual requirements for it, and then give you some time to start, brainstorming. Juliet's shaking her head no.
This is too fast.
Is it?
I couldn't believe
not
it.
ready.
You guys have until
Unreal.
like June 19th though. So you have a ton of time. But the capstone is like at least twice as big as a normal project, probably like 3 times as big. So it will take a lot more time.
Cool.
Yep.
To end. Home stretch.
It's going so fast.
I know.
It'll be cool though. I'm excited for you guys. Has anybody heard from Career Services yet?
Mm-mm.
Okay. I'm going to check on that because I think you guys should have heard from them by now. I think you
What?
start kind of talking to them and you actually get access to a different curriculum on Learn that's all like career stuff. So you go through lessons and you do activities and stuff for that. So I'll check on that tomorrow and maybe get you guys access and get the ball rolling on that.
We have access to the career stuff, just not the coach yet.
Oh, you do? Okay. Okay, so maybe the coach comes just a little bit later. So I'd recommend maybe checking out the career track if you have it.
I don't.
If you go on,
You have to click on switch materials.
yeah, you go to curriculum, switch materials. I'm going to have a ton, but I think it's like career track or
Career prep.
I forget what it's called. Career prep, yeah.
I do not have it.
Yeah, so it should be this one here. Because this is you guys, 812.
Yeah, I don't have access to that.
Okay. Does anyone else not have access?
After graduation, the Learn core environment will still be available to us for a period of time, right?
Yeah. I forget how long. I mean, I think it's a pretty long time.
Cool.
Or it might even be like indefinitely. I forget. But yeah, okay, I'll check on that then. Does anybody have any questions on anything? Any concerns? I know this mod's a lot. Things are moving quickly, but you're going to have a ton of time for the capstone, so it'll be okay. All right.